Evolution has had roughly 6 to 7 million years to work on the human spine since we split from our last common ancestor with chimps. That's plenty of time to fix a design flaw. So why does one of the most common medical complaints in the world come standard, built right into the human body plan? Your spine wasn't designed from scratch to hold you upright. It was inherited, then repurposed. For most of vertebrate history, a spine's job was to work like a horizontal beam, suspended between four legs, roughly the way a suspension bridge distributes weight between two supports. Picture a dog or a horse. Their spine mostly handles the same kind of bending and stretching forces you'd see in a beam. Then, somewhere around 6 to 7 million years ago, our ancestors stood up. And that same beam suddenly had to do something it was never originally built for: stack straight up, vertically, and carry the entire compressive weight of everything above it, straight down, onto two legs all day, every day, for decades. That's not a small tweak. That's closer to taking a bridge and asking it to also function as a load-bearing column, without redesigning it from the ground up. So how did evolution even attempt to solve that? The fix evolution landed on was elegant. On paper, your spine isn't straight. It curves in an S shape, alternating forward and backward through your neck, upper back, and lower back. That curve isn't decorative. It's what keeps your center of gravity balanced directly over your hips, instead of pitching your whole upper body forward. And this wasn't a modern human innovation either. Even some of our much older ancestors, going back millions of years, already show early signs of that lower back curve in their fossilized vertebrae. This adaptation has been under construction for an extremely long time. Sounds like a solved problem, right? A functional curve, doing its job. Except that curve comes with a catch that most people never hear about. Researchers studying human, chimpanzee, and orangutan vertebrae found something specific. The exact shape of individual vertebrae varies from person to person, and that variation isn't random. Some people's lower vertebrae are shaped in a way that's fully adapted to upright walking. Others, for reasons of individual variation, have vertebrae shaped closer to what you'd find in a knuckle-walking chimpanzee, even though they're just as human and just as upright. And the people whose vertebrae land closer to that ancestral chimp-like shape are significantly more likely to show signs of disc herniation. Not a small correlation, a meaningfully strong one replicated across multiple studies using both old skeletal remains and 3D bone scans. Picture two people, Bob and Alice, both healthy, both walking upright their whole lives. Bob's lower vertebrae happen to be shaped almost perfectly for the compressive stresses of bipedal walking. Alice's are shaped just slightly closer to the ancestral four-legged version. Same species, same lifestyle, same posture. But Alice is carrying a spine that's still partway through an unfinished renovation, and her discs pay the price for it. So evolution didn't fail to solve this problem. It's still actively in the process of solving it, vertebra by vertebra, generation by generation. Some of us are just further along in that renovation than others, and disc herniation isn't even the only signature of this unfinished renovation. There's a specific kind of stress fracture called spondylolysis, where a small bony bridge in the back of a vertebra cracks under repeated load, sometimes letting one vertebra slip slightly forward over the one below it. Researchers studying the evolution of the human lower spine have connected this fracture directly to the mechanical demands of walking upright on two legs. And it shows up in the human skeletal record far more often than in our quadrupedal relatives. It's essentially a stress crack, forming in exactly the location you'd expect if a structure built for horizontal loading were suddenly asked to bear weight vertically instead. Which raises the obvious follow-up. If this fix has been in progress for millions of years already, why hasn't it finished? Astronauts are a walking, orbiting demonstration of exactly how much work gravity is quietly doing to your spine every single day of your life. Send a person to the International Space Station for several months, and they come home measurably taller. We're talking as much as 5 centimeters, roughly 2 inches on a 6-foot frame. That's not muscle growth. That's your spine, freed from gravity for the first time in your life, stretching out and straightening slightly, the way it was never able to on Earth. And it comes at a real cost. NASA has documented that the muscles supporting the spine noticeably weaken in microgravity, since they're no longer working constantly just to keep you upright against gravity. Roughly half of astronauts report back pain during their missions. And in the months after they land, astronauts face a documented risk of disc herniation that's been measured at over 4 times higher than in matched non-astronaut adults. Think about what that actually proves. Take away the one force your spine has spent millions of years slowly adapting to fight, even briefly, and the whole structure destabilizes almost immediately once it has to cope with gravity again. Your spine isn't just under construction, it's under constant active maintenance, propped up moment to moment by muscles fighting gravity, so the underlying architecture doesn't have to be perfect. And here's the quieter, earthbound version of the same story. Starting around age 30, the discs between your vertebrae begin losing water content and gradually compressing, and most people measurably shorten by around 1 centimeter per decade for the rest of their life. You are right now on a very slow, very literal descent, the exact mirror image of what happens to an astronaut in freefall. Gravity built the problem. Gravity also never lets up long enough for evolution to declare the renovation finished. Evolution doesn't optimize for comfort. It doesn't optimize for your 50s, 60s, or 80s. It optimizes almost entirely for one thing: whether you survive long enough to reproduce and successfully raise offspring who do the same. And here's the detail that matters most. Global health data shows that back pain cases and disability from it climb steadily with age, peaking somewhere between 50 and 85 years old. That's well past the reproductive window for most of human evolutionary history. A spinal design flaw that mostly shows up decades after you've already had children is nearly invisible to natural selection. It doesn't get selected against because it isn't stopping anyone from passing on their genes. It's the same blind spot behind a lot of so-called design flaws in the human body. Evolution isn't an engineer chasing perfection. It's closer to a contractor who stops renovating the moment the building is functional enough to pass the one inspection that actually counts. And it's not just about timing. There's a genuine structural trade-off buried in here too. For a long time, the leading explanation for human childbirth being so difficult was that the female pelvis had to stay narrow for efficient upright walking, directly competing against the width needed to deliver a large-brained baby. That's a trade-off that would put real pressure on pelvis and spine shape simultaneously. Except more recent research has actually challenged that entire idea. A widely cited alternative hypothesis argues that childbirth timing may have much more to do with a mother's metabolic limits during pregnancy than with pelvis width at all, and that there's surprisingly little hard evidence tying a wider pelvis to any real cost in walking efficiency. So even the classic explanation for why the pelvis, and by extension the spine, can't just get wider and more stable, turns out to be a live, contested argument in its own right. This entire field seems to specialize in confidently taught explanations that don't hold up as well as advertised once someone actually goes looking for the evidence. Evolution took a structure built over hundreds of millions of years for walking on 4 legs, stood it straight up on 2, and has been quietly patching the gaps ever since, one curve, one vertebra, one generation at a time. It never needed to finish the job. It only needed you to survive long enough to pass the blueprint along. which means somewhere down the line, someone's spine is going to be a little more finished than yours is, but it just isn't going to be you.